used to, right? I will ask persons as you come in to drop your name in the chat, please. So everybody, please indicate your name in the chat. That's the attendance register. So you do that quietly to register yourself while you're coming. All right. So, moment about a force, right? That's today objective of the lesson, to understand and define moment and determine the moment of a force in the 2D and the 3D case, right? So we look at the application of forces. So for example, somebody driving a car, and what is the net effect of the two forces on the wheel? So we see in this case here, you have your left hand and the right hand, one going backward and one going forward. And so I could ask you, what is the coupling moment? So the coupling moment for any one of them would be where your hand is, and you ignore the other force. So let's say you want to find the coupling moment. Consider here as your pivoting point, right? I will consider an F up here. It will be F times the distance here, so that will be your coupling moment. And vice versa, you would find that this coupling moment is going in the what? Anti-clockwise moment, right? And then now, if you were to do similar to this one, take here as a pivoting point. This is your perpendicular distance, and that's your force. This is also a coupling moment. So the total net effect of those would be summing in this case. So if they ask what is the net effect of the two forces on the wheel, so you could actually sum the total coupling moment on the wheel, right? But you do not, to do coupling when you have two equal forces applied at this same distance apart, you never normally apply both of them at the same time. You consider one force at a time from its perpendicular distance. And you also take into consideration the turning effect. All right. Now, what about this application? So you have your log tool, and you intend to pull the log on your vehicle. Depending on which direction you're going, I should think that if you're going if you're going clockwise, you're tightening, and anti-clockwise is pulling, right? So if I remember it correctly, so I'm assuming if you go anti-clockwise here, so you're pulling. If you're going down with your force, so you're actually operating. Which plane are you in? You're operating in the ZY plane, and I'll get to that in a moment. But you're operating your hand in the vertical plane, pushing it down. And so I would say that you're operating in one plane, right? And I say, what is the effect of the 30 force on the lug nut? So there is an effect of it, a turning effect that will happen. So you're pushing your hand down, but what is the distance from your operating point? So those are some of the considerations we think about. So we think about the plane that you're operating your hand in, and what is happening in the next, what's the net effect of that, where something is going to turn here. Are you turning in the same plane? So these are some of the considerations that we think about, Charlie. I will come to it. So now, in the 2D frame that you are used to, let's consider that you see a plumber come to your house, and he take his pipe wrench, and he's going to make, let's say that he's a hole in this, and you have a whole pipe. You have a whole galvanized pipe, and he takes his tool, right, his pipe wrench, and he puts it on to the pipe, tighten it up, using the gauge here, tighten it up to the pipe. Now the pipe happens to be in the vertical frame, point of frame, right, reference point in the Z direction, and he is now operating in another plane, which is going to be your horizontal plane. So he's operating in the horizontal plane. And so the distance from you is pivoting point, which is O, which is right at the center of the pipe here. And he pushes on in that direction, meaning that he's going to push it in the direction of that force times some distance here. Then we have to look at, to consider that this is a rigid body, which has some dimension, unlike some particles. So it's a rigid body in these circumstances. The moment of the force about the point provides a measurement of the tendency of the rotation. And sometimes we call the same thing we spoke about earlier as the torque. Well, coupling and torque are different and same. It depends on the application. So this is sometimes called the torque moment around it. So you get a turning effect. All right. Now, one of the considerations in the 2D case is the magnitude of the moment. So the magnitude of the moment that you're used to when we say we find the moment of something is force times some perpendicular distance. And in, for example, in this direction, we see that it is turning in counterclockwise direction, right? So you have counterclock and you have clockwise. So it is turning counterclockwise direction. And so we can see that there's a force pushing it in some plane, right? As from some distance from original point. And it is shown that D is the distance from the point to the force, to the reference, to the force, to the line of action of the force. The line of action is the dotted red line, right, of the force. So the 2D direction of the moment is either clockwise or counterclockwise, depends on your determination, right? Or what we tell you the body is rotating. So sometimes you are given the direction that is rotating. Right? In fact, I should say all the way there's a direction of rotation. You need to assume which one is positive and which one is negative based on convention. All right. So another scenario here now, 2D frame, you could have a body here. A force is being applied. And when the force is being applied about some point D, right? So you see the line of action of the force. It has some origin coming from the origin point to the force line, which is D. However, often it is easier to look at components of the force. So this force will have component in the X and Y direction. So, and therefore we can solve for D. So that's one way of looking at it. All right. And so in a case like these now, you could also look at it in terms of A and B, which is a triangle form. Out of all of this scenario, you could look at it, let's say you never think about component, you could also think about it in terms of forming, using some triangle measurements. So you'll have two right angle triangles. You could go ahead and you could say, oh, well, I have A, I have B, I could find the hypotenuse. And then after that, you could find the angle, subtended alpha, right? And then you could go ahead now, finding that you have hypotenuse, you find beta, right? And so a number of things would come into play here. At the end of that, you could find alpha and beta will give you a theta. And theta is also any line that touch the force line, right? And so theta here, this line here is this angle here is equal to this angle here. And similarly, any line that touches this and this, these are two corresponding angles, while that is alternate angles, right? Because they meet at the same point. This is that direction, this is here. So this angle is equal to that one. So you could use your trigonometry and do it. But as I said before, you could use component instead. So if you're using component, then we could simply say that about O, F will have components in the X direction, A, and it will have component in the Y direction, right? Noting that it have an angle of theta there. So we could approach it from that point and say that the moment about y is fy times a minus fx times b, using the counterclockwise direction as positive, right? And I will show you more about that shortly. So what we're saying here, some of you may not understand this. So what we're really doing is, this is the origin, right at red here, where it is right at red here, where you're rotating around this point here. So let's say that there's a distance coming here. This is in the x direction. And we could say for you to take moment about A, this is you have a component of your force coming up this direction, not drawing it too correct. I must ask you to excuse me because I'm having a little bit of challenge. So I have to change my seating arrangement. So please bear with me a little bit. Right, if I was in the classroom standing up, it would have been much easier to deliver this lecture. So I have to be sitting down, which I'm having some issues with. So if you have any issues with not understanding, you stop me. I'll try my best. And if any time I may have to take a little bit a break because I'm having a posture issue a little bit here. So I'm just being very upfront with you. Right? If you may say that I'm not drawing right, I have to be changing my seating position. Moment. All right. So here is a distance here A, and this distance here is a component in the direction. So this direction here is in the direction of this Fy component, while this is f of x. F of x is in that direction. And so to get the moment around here, this is would be your distance, perpendicular distance to the force. The component is going up, that's Fy, and the perpendicular form here. If you were to rest your compass, where is it now that I should show? If you rest your compass right here at the red and put the marking point here, and you're rotating, then you would see that your moment is going that way. If you're going counterclockwise, because the force is going up, so it would give you a curve moment going in the anti-clockwise direction. Anybody want a clarity there? So you'll be going from here to here. Open your compass out to here, right? Compass point will be at the red, and you will stretch it out to here, and you're rotating. Because the force is going up, you're rotating it that way. So therefore, you'll get a positive. Anti-clockwise is positive. And for the other one, this is your force line coming across here. Right? That is your line of action of your force. Your distance from the origin is here still. And then you put your compass point right here. And so the force is going forward. So you'll be turning it this way. So that will give you an anti-clockwise. So this is why we get in that. And we assume anti-clockwise, that will give you clockwise, pardon me. And clockwise is minus. Anti-clockwise is positive, clockwise is minus. So they are going in opposite direction. So that is why one force is minus. Right? So the sign is what tell you whether or not we get that plus or minus. Right? Using component of the force. So we can determine rotation by imagining the body pinned at O and deciding which way the body would rotate because of the force. So we can see that Fy component is going anti-clockwise, while the f of x component is going clockwise. And so that one is minus. All right. Any question you can ask. All right, so we're gonna move forward now. Now, all right, I'm having a problem with my banner here. Trying to get it out of the way so that I can see what is happening. All right. Now, the moment in 3D, right? So 3D moment is not given in clockwise or CCW mean counterclockwise direction. It is stated as a sense, right, for the vector. Now, so we go to what we call it right-hand rule. Some people call it right-hand grip rule, right? And so we're going to look at all of the axes and try to make it understand. So we're going to take the right-hand grip rule, and we want to take one axis at a time. So we're going to look, for example, at the x-axis. So the x-axis, when your thumb is pointing in the direction, so your thumb is pointing in the direction of your moment, where you get your moment, and the direction of your hand now, note the direction of your hand, where your fingers are, the rotation will be the direction of your fingers. And so that is a sense of where your plane is. So if you see the plane is moving around, you're moving here. Let me point to it. You're moving here. Come on, here's my pointer. Come on. So you're coming here, rotating this way. Your finger is pointing in this direction, counterclockwise. Let's say that it is counterclockwise, right? But it is rotating around the axis in this positive sense. So we consider the direction of your finger we consider as positive, not counterclockwise, but it's in a positive sense. And so if you look now, your finger will represent a plane. So if your moment is in the x direction, yeah, your moment arm, which would be your force times its distance, is in a plane perpendicular to the x. Which plane is perpendicular to your x-axis? Can somebody tell me a plane that is perpendicular to your x-axis? Here, you have three planes. You have xy plane, yz, and you have the xz. Can somebody tell me which plane is perpendicular to your x-axis, please? Anybody?
XZ.
XZ? No, it's not perpendicular to it. That's not the right one. Come again.
Why is it, sir?
YZ, the orange one. The orange one is perpendicular because in effect what you really have is this. So that is a plane as a YZ, and your x-axis is that way. So this is Z. Alright? Or you could even say Z is here. So that is Z. And this is your Y. Alright? And that is your X. So your finger, your thumb, your big finger is in the X direction, which represents your moment. And the sense of your moment and your moment now the body is going to be turning that way. So your moment is this way, coming in the X, positive X, and your turning effect of the moment positively is where you see the plus sign. And so as a result of that, this is positive Y coming this way. So the force will be over here in what we call the YZ plane. The force will be there. So you will have the force and you have the distance over there, if you understand it. So let's say that your force is right here. Argument's sake. This will be your force for argument's sake. And then your distance could be this distance here. So you'll have F times D, and you get your rotation, right? So you would get FD, right? Your body, so you get your body going that way, turning effect, right? And so you will be able to get your moment there. But where's your moment? The moment is always perpendicular to the plane. So the moment arm is the FD is in the Y is in this plane, YZ plane, right? While the actual moment itself is perpendicular to that moment, right? So this is your moment down here. And this moment is in the X direction, right? And it's turning in the positive sense. So you can see you use the right hand grip rule to find out which direction it is rotating. Once you put the hand there and with the direction of your fingers going around, right? Direction of your fingers curling around, that's the direction of your moment, right? So you can have a sense there. All right. Let's any question there? Let's go continue. And similarly, right? Let's consider force parallel to an axis cannot cause rotation about that axis. So if the force is parallel to the axis, so for example, F1x cannot cause rotation. See it here? Cannot cause rotation in the x direction. Right? Force passing through an axis cannot cause rotation. Where it is? F2Z. Where's F2Z? See it here? So it's passing through the axis. It cannot cause it passing through an axis cannot cause rotation. So both this one and this one cannot cause rotation. Right? F1Z is this, and F2Z is this one. So it's passing through the axis and it cannot cause rotation. Force in the 2D frame, which is YZ, which is this blue here, cause rotation about the x-axis. So when you're in this plane here, you're rotating around only in the x-axis. That's what I'm saying. So it's clarity to what the slide I was talking about. Let's continue. Similarly, in the y direction, right? If you have a moment in your force in the 2D XZ plane, which is the red plane here now, must cause rotation in the y direction, right? So it means that this plane is the plane that we're talking about is the XZ plane, which is a red plane, and your moment is going in the y direction, and your sense of rotation. You see your hand? See your finger, big thumb is there, and your finger will show you direction, your sense of rotation. Your sense of rotation is this way. Can I draw it? So you'll have something like that coming around. When you see it, so that's your sense of rotation, positive. Right? So that's what's happening in that plane. What about the next plane? Did I skip one? Like I may have. Right, this one here. So we said here, for force parallel to the x-axis cannot cause rotation about the that axis. So F1Z, where's F1Z now? F1Z is right here. It's parallel to an axis, cannot cause rotation about that axis. So it cannot cause rotation about it. So it's parallel to the axis, couldn't cause rotation. Force passing through an axis cannot cause rotation in the F2x. Where's F2x now? F2x is here. So it's passing through an axis. It passes right through the axis. It don't do anything. And so we can say here that for you, if you're having moment in this plane, and in the Z plane, is a result of your XY plane, that your moment is operating down here in the green. So force in the 2D XY plane must cause rotation about the Z axis. Any question there? Very, very important. All right. All right. Let's continue. Like you all understand. Okay. All right. So we have gone through this around. So if your moment is in the X, it means that your moment arm is operating in the YZ plane up here in the 2D plane. All right. Remember that. When you reach a rigid body, these become important. And if you're in the Y, it means that you're operating in the XZ plane. All right. Is that clear?
Wait,
Anybody?
sir, could you just go back to the diagrams that you were showing? Okay, so you're saying if you're operating so like for the red plane, the rotation would be on the y-axis positive?
Well, we're saying two things we're saying here. So in the plane that you have your moment arm, your force and your perpendicular distant. So for example, let's say that your force is in argument, say your force is in the Z direction. and your moment arm is in the X. As a result of that, you can get a turning in the Y direction, which is perpendicular to that plane. So you don't have a moment, your moment times your distance occur in one plane, and your so your moment arm, the force times distance is gonna occur in one plane, while the actual turning is gonna take place in a plane perpendicular to that plane, which in this case is the y-axis.
Okay.
You get me? So the red plane is perpendicular to the y.
Right.
Yeah. So that's what we're saying. And the sense of direction, or you know the direction of its turning, you have to use the right hand grip rule. Your thumb point in the direction of the y there, in that case. All right. And your finger rotate, your finger show you the direction of rotation. All right, so once the finger is going in that direction, that's where your rotation would be, based on the force and whatever. All right, based on what you're doing. All right, okay. So what we're actually saying here now, that was 2D being applied in a 3D frame. Now, all examples are not going to be so straightforward, and we have to move on from that rule of thumb now to another level, right? So the other realm that we're going to move to now is the vector formulation. So we may have a force in a 3D frame. A result of having a force in a 3D frame, that force will have component in all direction of in the y direction, the z direction, and the x direction from the origin. So we have a force and it has components somewhere out in space. Its point where that force is going to turn, its turning point will have to be looked at from the origin. So a line from the origin touching that force would be this R here. Can you see that R? R is some distance from an origin touching that force, which is this force is right here. And that force here has component in the Z, the Y, and the X. And so similarly, this R here will have component in the X, Y, and Z direction. So it will have direction, it will have component in the Y, X, Z direction. Two of them. Right? So if F has X, Y, and Z component, and both the distance, it's distant, and now we can't call it perpendicular distance because it's a vector distance touching F. Right? In this scenario over here, it shows you that you have a plane. You have a force in a plane. Some distance touching it out here, right? If you can see it better. And a result of this in this plane, have a vector distance touching your force will cause a moment, but it will cause a moment in a perpendicular frame. See here? Right angle frame, you have that moment. Can you see the moment? And can you see the rotation direction? Right? And so there is a moment in that plane, and you sense the moment you see it. All right? And you can see all the planes that are relevant there. So the moment in 3D can be calculated using scalar 2D approach, but it is difficult at times and very consuming. So if you were to do the 2D in a 3D frame, it will take you a whole lifetime. It's very difficult to do. So instead of that, mathematicians have come up with a formulation of what we call a vector cross product approach. All right? So this is how we come about this now. So in order to solve that complex vector problem, we come up with this formulation where we say that R can be converted to a vector form and also the force, where it can be R, your distance, can be placed into coordinate forms, I, J, and K, and similarly force can be placed in I. And so you can find your moment of a body. A moment is also a vector quantity as magnitude and direction, And so it also can be represented in I, J, and K format. And so the vector cross product is what helps you in a 3D to define your moment. And so they come up with this formula to say the moment around the origin in this scenario is going to be some vector quantity R times F. And it is not commutative, meaning that F is not times R. That's wrong. If I ask you for the vector cross product and you go force times R, that is wrong, 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 wrong. Never ever put the force before the R. So this is how it is donated. And sometimes we put all things like this in quiz because if you write F times R is wrong versus R times F, right? This is not A times B is not equal to B times A. So we are saying F times R is not the same thing as R times F because this is a vector quantity. Now here R is a positive vector from the origin and the point of rotation from O to any point on that line F, right? As I said to you before. And so this is now what we're going into what we call a cross product. So in the cross product sense, your right hand grip rule shows you in cross product that if you have two vectors in a plane, A and B, and you can see their sense together, so you can see that they have a distance apart, theta. Their thumb is in the direction of the moment vector, resulting moment vector, which is C. And so the cross product of A times B means that you can consider the unit vector in the direction of C, right? Where C is going to be A times B sine theta. If you remember about dot product, so for your dot product, when it is A times B, also say that you could also get the perpendicular of that line. Rather than getting just the parallel line in projection of a vector, you got a parallel line to the where the line is projected to the vector, right? To the direction of that vector. So in general, the cross product of two vectors AB result in another vector C. Let me just go through this. So A and B is the magnitude and the direction of a resulting vector. It can be written. And so C is A times B is the same thing as AB sine theta C. And I want to use this to recall that when you're working, it's probably be careful with your vector. Don't use a scalar value of the vector. It must be the vector times a vector in this case. All right, so I want to point out that. And then you have AB, which will be its modulus times sine theta times the unit vector C. All right, so I'll speak more about that. So the unit vector C is the unit vector perpendicular to both A and B, which is right here, all right, as shown, or to the plane containing A times the vector P. All right, so we say more about that. The cross product rule is different from dot product rule. All right, remember I was telling you. So here we're looking at it now. So the right hand grip rule is a useful tool to determine the direction of the vector resulting from the cross product. For example, I times J is equals to K. Right? Remember before I was telling you that I times J give you 0 in dot product. In cross product it's different. I times J give you K. So note that the vector crossed in itself is 0. So in the dot product, I went with parallel vector. Once it's a parallel vector, I times I in this case for cross product is 0. But in dot product it would have been 1. I times I give you 1. So we are totally shift our own so we shift in terms of so remember this subject has an alignment with mathematics, if you notice that. So you must have an appreciation. Right? So what we're actually saying here now, if you I times J, so you have a vector I times a vector J, it gives a vector K in cross product. And so you can look at it. If you have positive K times positive I, So positive I, sorry, positive I times positive J, taking these two, it give you a positive K. And you see the direction of rotation. So positive mean you're going in the positive direction I times this, give you a positive this. But if you go the opposite direction, so you can get the negative of them, but you have to go the opposite direction. Right? And that's what also this is showing. So if you go the opposite direction, you get them negative. So you will say K times J will be negative, give you a negative I, for example. All right, so you have to be, that's cross product is not commutative. So remember that, please. Very, very important. So here now we come up with a cross product mathematical approach. So in order to utilize your cross product, we go into what we call the 3D matrix. All right, where we say vector A times vector B give you a 3D matrix. And so we write up the top I, J, and K. And so A here is always written up here, right? And B is always written down the bottom. So the cross product is simply the determinant of the matrix. So in order to do the cross product, you will be doing what we call the determinant. And we'll be using the 2D, 2x2 determinant method here, right? And there are some parallel between what the term of 2D that you learned, the matrix that you learned before. Something a little bit similar, but we're going to take you to it now. So each component can be determined by using 2x2 determinant. So in this here now, to get the determinant, I will consider I. So for consider I, you would eliminate the first column because you would not include the I column. Nor would you include anything up here except I itself. Then was the circle I. So look at that one. So for I, in order to get the determinant, we go leading diagonal and non-leading diagonal. So we exclude that the first row, first column, and then we go here first now. So for leading one, we go AY times BZ, sorry. That's BZ. All right, so you go here first, and then secondly you come AZ times BY. So you know this is minus, and that is a positive. Always a positive. So remember that. I is a positive. In the second one, this is positive, this is minus, this is positive. So we'll tell you what that come from. So here now we put in a minus J here. Always put in a minus J. And note the sign. So a negative sign you must note. Don't leave it out. And so we go. So the column that you're moving to now is J. So you put this second column, you exit out. First row except the J. So you put minus J there because this is plus, minus, plus. And then now you're going to do the same thing. The column that are interested in you is the I and the K column. Anybody who understand, please tell me. So we're going A, X, B, Z, same leading diagonal, A, X, B, Z. And then we go, the next one now, the non-leading is A, Z, B, X, which is minus. When you finish this, your sign will change based on the minus out here. Whatever you get in here will be changed depending on what you have inside here on the outside side, right? And similarly, for K, you exclude K, exclude everything except K up here, put back K, and you're going to do the same thing. So this is leading, non-leading. So this is A, what is that now? A, X, B, Y, first one. Then you go AY, BX, right? And so you would have found the determinant, and this would help you now to find the moment. So your moment here now, it says, so using the cross product, the moment can be expressed as positive cross force, which is the moment about the origin, is R times F. And so you must always write your matrix in this form. This represents the Cartesian of the axis. This is X, Y, and Z. The first row represents the distance, position vector R. So R is your position vector leading from the origin to the force. And the last line is your force line in Cartesian. Right? So by expanding the above equation with a 2 by 2 determinant, we can get simply what the moment, and the moment can be either Newton meter or pound foot or whatever, depending on the unit. So you would typically get something like this. This is always going to be minus, must put here. This is plus, this is plus. So that's a convention. The physical meaning of the above equation becomes evident by considering the force component separately and using 2D formulation. Any question there? Any question there? All right. Now, let's step it down a little bit. We're going to step it up back again, you know, but we'll step it down a little bit. Let's talk a little bit here. So, what time we have here? Okay, almost an hour. So, we have a frame here. It says given a 400 Newton force is applied to the frame and the angle is 20 degrees, find the moment of the force about A. So this is a simple one, all right? So you have a simple frame, it is pinned at A, and the frame is out there. But then now you apply a force out at the tip of it. All right, cool. They said that I want the moment about A. Where's A? A is right here. Right at this point. Everybody see my pointer? Everybody see the pointer? Can somebody acknowledge me, please? Thank you. Do you see my pointer?
Yes, sir.
Yes, sir.
Thank you. Bless you. You can open your mic and you can ask a question, please. Don't be shy. So the plan is you're going to resolve the force along X and Y. All right, you're going to resolve this force here in X and Y axis. And then you're going to determine the moment about A using the scalar analysis. So let's jump into it. Let's jump into it. All right. So first of all, we know that F here can be split into component. Component in the X, which is red, and component in the Y, which is blue. It so happens that these two components are going in the negative direction. I only put the minus sign just to show you that I'm writing the component of the force properly. But it is relevant to what I am doing in terms of taking my moment here. So I just put them, we put them as minus here. So we know that up direction, convention is positive. So if it's going down, it's minus. And going this way, the convention, so if you're going to the right, it's positive. But these forces are doing the opposite. So we put them in. All right. So those are the components. All right. The next step is to take moment about the A where we say the body is turning. A here. First thing we establish is a convention. Taking anti-clockwise direction as positive. This is what this sign here means. Anti-clockwise is spin opposite to clockwise. And we say that that is positive. And the moment is about A. So we write it M lowercase a equals. So let's go on and take the moment now. And if you don't understand while I'm going through, please, for heaven's sake, stop me. I have a stylus here. I can stop and I can explain. So I have my stylus here and I will write on my stylus now. So, all right. Now look at it. A is right here. All right. Good. A is there. And the first moment we're going to take, we're going to consider the 400 sine 20. That is supposed to be what now? So if 400 sine 20 is the Y component of the force. Y component of the force is going down where? Is it coming down in the blue? Let me see if I can get the blue. So it's coming down in this direction. Can you see what I'm talking? It's coming down in that direction. Right? And it's distant from A is what? 3 meters. Everybody see that? So it tack right along going out to it. A line touch the force out there. And where's this perpendicular? Right here. And its turning point is down at A. Now, if it's going to turn it, you put your compass down at A and you touch it out here, so it's going to give you this. And that is what? Where is the moment? The moment is going to be anti-clockwise. So that component is going to be turning it anti-clockwise, and we say already say our convention anti-clockwise is positive. So therefore 400 sine 20 times 3. All right? And we're done. That's the first one. The second component now is the red going this direction. And you see him ticking, tick, tick, going all that way. Right? So it's continue. Right? So it's line of action continue in that direction. Eh? You remember we talk about line of action? So the force line of action is continuing that way. What's the distance from A is what? 2. So it have a right, it make a right angle. See, it touch right up to here. And it touch the force line right here. And so it have a right angle right here. Right? And what is the right angle? Where you touch the force? So if you were to put your compass point at A and touch the marking point of your compass right up where it meets the line, right where it intersects with it, it will give you a turning moment going this direction. Can you see that? Well, it wouldn't be so steep. So truthfully, it wouldn't be so steep, really and truly. I think that's a little bit too steep. Can I erase that? Let me see. It's a little bit too steep. It would have been a little bit more, I do that. It would be a little bit more something like this. I think probably a little bit more like that, right? Based on the arc, it would have been something like that. And both of them incidentally are going in the anti-clockwise direction. So it's 400 cos 30 times 2. And so when you add them together, they'll be giving you 116 Newton meter in the counterclockwise direction. So if you notice, I didn't consider the sign here and here when I'm taking the moment. You're not to consider those signs, you have to consider the direction that the body is turning to get your sign. So at this, one of them turn clockwise, we'd have to put minus sign. But they are both going into the anti-clockwise direction for the 2D free. Remember? All right, I'm moving on.
Sir, can you repeat that, please?
Okay. All right, what I'm simply saying to you, even though I show you with the two statements there that those two components are actually going in the negative direction. When I'm taking the moment, I do not consider the minus, the signs of them. I look at the direction that the components are going. Because if I was to carry them minus, I would be doubling up signs in it, which would be wrong. I just consider the component themselves to know that it have a component and I look the direction that the component is taking it. So one, I look the direction where the red is going. The red is going to the negative. The blue is coming down into the negative y direction. So the red is going negative x, the blue is going negative y. That's all I'm showing you here. When I'm taking a moment, I just consider the component and look at the direction that it is turning to get my sign. So one sign, I already established the convention over here that the convention that I'm using, everything going in the counterclockwise is positive. So that means anything that is going in the clockwise is the clockwise is going to be minus. So we have established that already. So when you start out, you have to make a statement. Remember now we're using equilibrium equation. So it's sum of a moment about A is equal to 0, and I put this. Anti-clockwise is positive. That's a statement that you make before. That's what should be over here, but it's kind of not right too good. So that's a statement. All right? And so we have now used and saying 400 sine 20 coming down times 3, right? And I show you the 3 turns. So it's turn counterclockwise, and similar 400 cos 20 turning again. But so I'm that both of them are turning the same sense. All right? So all you have to think, it's like you have your big thumb and they take one of your finger and touch out to that point. And then you look at the direction where the force is going. And you spin that direction to get your balance. So wherever, so you can use your big finger. If I was in the class, I would put my big finger where my turning is. And span my finger out using that to the distance, to where the force is. And then I rotate like I'm a compass. with your finger. And you could just use that in your head to see what direction you're turning. So if I hope that analogy helps you to figure it out. It's quite simple. All right? And once you do more of it, and you have to do a lot of it when we get to stresses. So you'll understand. All right? You'll get more practice, and I'll give you more in this section. All right. So we continue. All right. Now I'm gonna skip over some of my problem because I don't have all of the time to go through everyone. There's another one here too. The same principle applies here. This is another 2D. And so this 2D, you have a spanner. You have a force applying to the spanner. A force of 40. It has two components. The 40 can be broken down into components parallel into the y direction and parallel and similar in the x direction. So you can see the x direction. The red is it. This one is in the x. This one is in the y direction. Right? And they similarly go in the same direction. So it says that the 40 force is applied to the wrench and the moment about O. You must resolve them into components, which you can do there because you have the angle. And then you identify their components, right? 40 and so on. So maybe and truly I can take out that sign here. So those are the components, right? I could actually move those signs around here because it may confuse some of the students. And then you take the moment around O, which is O here, right? And so when you take the moment about O, you're gonna look for the sense now. Anticlockwise being final, so that is gonna turn the body into a anticlockwise direction. Let me look good. So yeah. So that is going to be minus. Let me see if this is correct. So if this is here, this is gonna turn it minus 40 here. Let us check that. Right. Let's look at this one here. And then you have the other one. So one is going to be plus, one is going to be minus. Let's see which one is, if I'm looking carefully. The sign is going to be the 20. So the sign is positive. Because it's going in anticlockwise direction. So it's 40 sign going that way. It's going to turn the body into an anticlockwise direction times the distance, perpendicular distance here is 20. So that is going to turn it into the anticlockwise direction. Yeah? Correct? This one now is going to turn the body in the clockwise. So it's going to be, this one is going to be 40 cos 20, turn it into the clockwise times its perpendicular distance about O. All right, so when it comes down, it's going to cross the line at 200. And so this becomes minus. So this is clockwise. First one is clockwise and the second one is anti-clockwise. When you add both of them, you get minus 7107 millimeter. And then you can convert the millimeter to meter and you get minus 7.11 Newton. So that is similar, right? All right. Next one. All right. What about so today I had a class today and I was marking up this one on 1 second. I want to discard this. I want to jump off all of that. All right, let's go back. So so for you now, all right. So for the 3D frame now, let's look at a problem. So let's say that let me go to where the problem starts. Let's tell you what the problem is. I'm looking for the problem. Where is it? All right. All right. So the problem says here, given that A is in this case 3 inches, B is 6, and C is 2 inches. Find the moment of F about P. So you find the moment about P. Right? Moment of F, the force about a point P. Now the point P is lying on the z-axis. Everybody see that? Right? So the plan is first you need to get your position vector of PA, because PA is a line that touches the force. So there's a force there which is given in Cartesian. You have to stretch a line from P to A, which touches the force, right? And that line is to find that line, we go into finding RPA, which is a position vector. So you establish your position vector to touch the force line, right? And after that, now you could determine the moment about P by applying your moment in 3D vector. So it's going to be R times F. Everybody observe it. So you determine R times F about P. This one right here. All right, so let's show you how it's done. So you go ahead and you would establish your position vector. You know your position vector of PA is going to be equals to A minus P. So you would establish your point A and you know point P. Right? Point P will be what? Can somebody tell me point P will be what? What are the components of point P? Quickly, somebody tell me the component of point P. You're supposed to be able to look at it now and tell me. What are the components of point P, class? No one? Anyone? Hello? 19 persons and nobody answered.
2,
What?
0, 0, 2, 0, I, 0, J, and 0, K.
Right. Good. Yeah, then that's so when you're taking so long for answer. And A now would have been, what's A?
Would it be 3, 6, and 2?
So you're saying this 3.
No, 3, 6, and 0.
3, 6, and what you said?
0.
Okay. Anybody disagree with him?
No, sir.
Okay, cool. He's right. So you would take away P from A, and then you would get back 3I, 6I minus 2. Yeah, simple. And so you now put it in this form where it is R times F. So you know that R is here and F is right here. Right? And you go ahead now and do your multiplication. So you would establish that your I. So I is positive, I minus J, right? And plus K. And you go ahead now and you could do your multiplication on each one of them and see if you can find the moment. So for the first one, you would for I, that wouldn't exist, column out. Only thing you need is the I, which you have. And you go, the leading one is 6 times minus 1, you get minus 6. Not true. And the next one now going this way, it will be minus 2 times 4, line 2, sorry, give you minus 4. You agree with that? Who disagree with that? And the next one, it's now, but on this one now, this one is tricky. Let me erase, let me try if I can erase something. Here's the eraser. Right again. All right, so for the next one, you would now, you exclude that column, except that you need the J. All right, so the column that you're interested in, the I and K now, because you're doing J. And so you will go 3, go that one first, so it's 3 times minus 1, minus 3, minus, and what do you get here? So now, minus 2 times 3 give you what? Minus 6, that's all. All right?
Yes, sir.
And then the last one now, if I can erase these, oh, where's my erase? We go again. And, so the last one, you'll exclude that column. Everything except only K you need. And then you have, so these are the 4 that you're interested in. And the leading column would be 3 times 2 give you what? 6 minus 6 times 3 give you 18. You agree? And so This one would end up to give you the first one. I put those equal sign too far out. I'm just gonna scratch them out. So the first one would give you what now? That would be -2, that's all. Agree?
Yes, sir.
First one will give you -2. This will give you +6. And -6 will give you a +3 inside the bracket. But you have a minus out here, so it give you ultimate give you -3 3J. Alright? Ultimately. And then the next one now, down here it will give you -12K. Alright? So this one will give you -2I. And so see you have them there. Oh, it's on the other slide. I keep doing that, but I forget that it work out on the other side. So see I have them there. So you multiply them and you put in minus and you pretty much get them. I discovered today that this sign was wrong. It's come down, it's minus here, never could translate down. Supposed to be minus. So you're supposed to have plus, minus, plus to get this. Alright? Let me see if that answer is for it. Let me just check. They're all minus. Yeah. So you should get minus or -3. Right. So that's just showing you how it works out with the multiplication. Alright, next one. Alright, now we're gonna look at what time we have. Right, I need about another 20 minutes of lecture and then we can go to the thing. But we will need to take a little break. Alright? And you guys need to participate. Alright. Next one. I don't want this tool here. This tool is not mine. Where is it from? Alright, next one. Don't know why that tool coming up, and I really don't need it. Still me. I don't really need it. Alright. I'm gonna work with it to see if it can work. I go have a right. Alright. So here we have, we're gonna look at the moment about an axis, which is totally different from what we're doing. So previously we were looking at the moment about a point. So you should here now this part of the unit 5. It says you have to determine moment of a force about an axis using scalar analysis and vector analysis. So there's something called scalar analysis and vector analysis. So let's move on. I'm gonna have to kill this. It's gonna code. So here now we can look at the force F. A person is creating a moment MA, like what we showed you before. The moment about a point, what portion of MA is used in turning the socket. So if it's during a socket about the point A, yeah, and this can be shown over here. Now the force F is created about moment O. So another scenario, let's say that you're doing force F is creating a moment O. How much of the moment about O acts to unscrew the pipe? So one is showing a moment about a point which you analyzed a while ago, and this one is telling you take a moment about another point. Right? And so you can look. I don't know if you can see it good, but look at it carefully. You have a force in the Z direction, -20, and you see a line touching it from the origin, which is RA, to that force line. Right? Now, so there are a number of things you can look at there, you can come up with. You can look at the force. You can get MA, for example, or MO, right, by doing a number of things here. You could find the moment as a result of it from one plane, right? So you could, if your force is in the Z direction, then your moment have to be in a plane perpendicular to it. So let's, for example, say that your moment is in the YZ plane. You know that it has to be into a plane that is totally perpendicular to it, for example. Let's jump on over here because that's just a diagram. We just talk a little bit about them. Briefly. Next one. So here now, this is known as a scalar analysis. If I can erase anything here. Hold on, I can't find any tool. If I get wrong, erase. Not seen erase. Come on. Okay. So for scalar analysis, recall at the moment of a force about any point, M is equal to force times distance, perpendicular, right? From the point to the force, having the line of action. This concept can be extended to find the moment of a force about an axis. All right? Not about a point anymore, more about an axis. All right? So in this case, we could actually look at the point 3 times the force. So let's say it is in the XY plane, for example. Then your turning effect would be in the Z plane. So if for this one here, let's say that your force going down in the Z direction, and your distance is in your X. So this will be your XZ plane. Then now your moment will take place in your Y plane, right? That's typically. So in this case, the perpendicular distance was explicitly stated, right? Now, in the figure above, the moment about the Y-axis would be my 20 times 0.3, which is 6. However, this calculation is not always trivial, and the vector analysis may be preferred. So you can actually do the 2D of it in some sense, but it's not going to be always that easy for you to analyze something like this, right? And that is just a trivial approach to it. And to find the next slide. And similar, you have what we call the vector analysis of a scenario like this. All right? So the goal is to find the moment of F about an axis. Where's the axis? AA axis. And you see the force down here. Can you see my pointer? Let me see if I can show the pointer. So let's say that you see where F is. Can you see the point? It might be very faint. This stand is coming down through here. O to A, where is the R coming down? That's the distance to F, right? It will produce a moment about O, which is RF, normally, all right? And you could see its direction along B prime B, right? The line B prime B, which is running across here. See it? B prime B, running across here. Now, so the first thing you compute the moment of F about some arbitrary axis. Arbitrary point that lies on the A prime, A prime A axis, which is the vertical one. Right? I'm having a little problem with my tool. Tool is all over the place. So you have this one is coming down here and here. I'm not using the pointer. Right? I'm gonna need to clean. Right? So you can find the moment about O, which is R times F. Now, based on that, we can say the moment along the axis A prime A is using the dot product, right? Recall that the dot product, recall that MO is a Cartesian vector. As you get the moment about the axis, which is MA, you use a unit vector along the particular axis times the moment about the origin. So that is UA times MA, and this is a dot product, not cross product. And so we'll show you what that means. This part here, you have to be careful here, very careful. So the vector analysis of that, all of this can be put into vector analysis now. Where your working part as dot product and working part, everything can be kind of put into a vector format. So you can write a matrix here where you put the unit vector in, where you used to have the I and your J and your K. You put that up there as your first row. Second row is your distance, your position vector, and the last row is your force. When you do this, so them say the above equation is also called a triple scalar product. So that's what we call this one, triple scalar product, right? And so in this equation, U is going to be your unit vector representing the unit vector along the axis A prime, which is a vertical one, or the position vector from any point on that particular axis to any point A on the line of action of the force, which is right here. If you can see where A is right here, right? And then F is the force vector, right? And so this is a lot for you to take in right there. All right, let's look at this now. All right, let's look at this here. So you have you're using a tool. All right, so a force is applied to a tool to open a gas valve. Right? You must find the magnitude of the moment of the force about the z-axis of the valve. All right, now look at this now. So your plan, we need to use the moment about the z-axis is going to be equals to the unit vector along the z-axis, and you dot it along the moment r times f. What are we saying? A lot of stuff here. So note that u is equal to 1k, that's unit vector. All right, and you know, so the note beside it is not always so straightforward that you can just spot out the unit vector. And the vector r is the position vector from A to B. So it's a position vector from A to B, right to where your arm is. All right. Force is already given in what? Cartesian. See it up here where the hand is. So you're applying your force up there. You're turning the tool. And down here the tool is and pulling the gas valve down at the point down here. Right? You can call that O down at the origin. And you can see clearly where Y is, clearly where X is. So you can see where you're operating from. Let's see how we visualize this. Come on. Sorry. All right. So here now, what we're really saying, your unit vector in the Z direction is 1k. It is 0, 0, 1k. Or your position vector, if you look carefully, where R is, AB is aligned to this distance down here. That's AB. And so because of that, in the plane, XY plane, you can get position. You can break up your position vector into a component in the Y and component in the X. And so it becomes 0.25 sine 30i. That is in the, this one is in the sine is in the X direction, and cos, this distance here, down here, so is in the Y direction, which is cos. So it's 0.25 cos. So you break up that component, that length, into X and Y for your position vector, right? And so you have it as 0.125 in the I and 0.2165 J in the Y direction. So that is your position vector, right? Right? You wish all position vector could be so straightforward. And then now your force is already given to you in Cartesian, so you don't have to worry about that. You could go ahead now and find a moment about. So this A is on your axis here, your Z axis. So you can find a moment about A. So you can proceed. Moment about A is going to be RA times F. And simply, this is your matrix. All right? And your matrices have I, J, K, first column, first row, sorry. Second row would be your position vector. So the Z will be 0, and all of these quantities 0.125, 0.216, and you write the K as 0. And so you put your force in the last row, minus 6, 20, 15. And then you proceed now to do the same thing that we did before. You have the I stationary. So the I is L stationary. First column L stationary from the I. And then you take the second term here, your determinant here, you go first row, first leading diagonal there. Then this one comes after that one is gonna be 0 there, right? So you only get 0.216515, which is the first part. Right? And the second one now, you're going to take only J column. Only the J column you're going to need. Did somebody mark it? Did somebody mark my table a while ago? Guys, I'm going to ask you not to do it when I'm teaching. Please. You might be tempted, but don't play with the devices. Because all of a sudden I see some stuff pop up. So the next one here, please, don't do that. I will know. But you're going to interfere with what I'm saying. All right. Let me go back to what I have to do. So you go back to your next column. I'm not gonna mark it up this time. I'm just gonna touch them. So so this is the J. You exclude everything away from that. So you'll be dealing with I and K. So it's 0.215 times 15. All right. And then the other one would be 0 times 60. So that will drop out. So you only have that. But remember now you have a minus that is waiting for you, minus J. So you have to put in that red there. See, red minus sign. And then the last one now you'll take your K, you'll exclude 0 and 15 in your last column. All right, and you only observe K. And then you'll be taking the determinant of 0.125, 0.216, and minus 60, minus 20. All right, that's those 4 components you're working with. And so you go ahead and 0.125 times 20, first one. And the leading one now would be 0.2165 times 60, right? But remember, it's a minus 60 and you have a minus here. So that will typically give you a plus. And then you work it out with this one. So you know everything is a 15.15 K. And so you get that moment there. So that is only start. That's the moment about A. But the moment about Z, the axis Z is different. The moment about axis is what you're really interested in. Trying to get my writer to work here. So so this is the Z axis. About there. So now to get it about the Z, you need a unit vector about the Z, which you know. Right? It was we had it, right? I think we had it. So we get your unit vector along the Z times MA, which you found a while ago. So you found this, you need to find that. You did this a while ago, right? So this is 0, 0, 1, K, yeah? 1. Always 1 K for that unit vector. And therefore you dot it with this one. To dot it with this one is going to be 0, I times 0, I. That's 0. So 0, 0, I times 3.247, I, 0. 0 J times 1.875 J, 0. And then the last one is going to be 1 times the 15. So therefore, that is the answer. Because look, you use your dot product here. Dot product. I times I is 1, but in this case is 0 times that whatever figure is there. And the same thing with the J. So you're using your dot product. So look, it might be confusing because you're using a dot product and cross product at the same time. The cross product is used for finding the moment about A. Moment about a point. The moment about the axis now is where you use your unit vector along the axis. So when you find about an axis, you need a unit vector about the axis. That's the only difference. And you also need to recognize a line from that axis that touches that force. That's the next thing that comes in. So it's 2 things you need to remember. A line from that axis that you want it from to the force. And very important, it is going in which direction? It's going from A to B. So R is A to B times this. Right? Very important. So a line coming from that axis touches this force here, because this force is somewhere along here. So this line touches out here. right? So those are the principles. All right. Any question there? Any question? I'm gone. Next one. All right. Another problem now. You have a force of 80 pounds acting along the edge dB in this scenario. The magnitude of the moment of this force about the axis AC. That's what they want. Moment about the force AC. Now, the plan is we need to use MA, right? MAC times the unit vector of AC. Which axis did they say you want? They say the force of 80 pounds acting along the edge, dB. They want it, and the axis that you find about is AC. So it means you need to find the unit vector along AC. And you have enough information so you can find the unit vector. Now to find the moment about that axis, you can go two directions. And you can typically do it this way. Let's take it one at a time. You can say find UAC, right? So you're gonna find the unit vector, which you know you find the position vector and divide by its modulus. Done. The next stage is to find a line from that axis to the force. How many lines? Can you tell me two lines that touches that line AC to the force line? Can somebody tell me two lines that touches it? Two position vector that touches the force and it touches the axis. Can somebody tell me two lines that touches the axis that we are thinking about, AC, and also touch the force line, which is dB? That's a question.
DA
Yeah?
and DC.
Yeah? There are three lines actually. Give me three of them. So AB is one. Give me another one.
You have AC, you have AB, you have
No man,
AD.
AC is not it. AC is the
DA,
axis. You go X. You have CB. And what is the CB?
yeah,
Yes.
DA and DC.
Not DA, is AB. You're going from the axis to the force. Remember, note the direction. Always from the axis to the force. So one of them is A to
AD.
D. AD is one of them. AB is one and CB is one. You see that? So in this case, we choose to use, so to find the moment about the axis MA, we say we can use the unit vector along the same axis, which is UAC, and then we are going to use the position vector AB times the force. You see that? That's one we choose to use. And so you also need to change the force into Cartesian. So you're going to have to find the position vector of what? dB. And to find the position vector of dB, everybody can do that by now. And then you multiply it by its position vector. No, when you get the position vector, you get the unit vector, and then you apply it. Because you know which formula this you'll be applying. What's the formula you'll be applying here? See there in front of your face, FdB is going to be equals to F scalar value times its unit vector of the, supposed to be dB. What did I write here a while ago? I don't think I write dB. All right, it's supposed to be dB. That is the formula. All right? So this is the vector formula. While that is a scalar force, part of the force. That's a scalar, this is a vector. You look at above. That's the formula they employ right here. All right? That's what you're doing. So this is a unit vector. Remember, all of this is unit vector. See it right there? And you get your force. You convert your force to vector from the scalar form. So it says it is given to you in scalar form. And then the last, you complete the triple scalar product. So let's look at it how it's done. All right, so you find the position vector of all of them. You find of AB, you find of AC, right? Because you need AC to get the unit vector of AC. And then you find this one here, which you just spoke about, dB, position vector. And so you can find the relevant unit vector of AC, which is the axis. The axis is here. What you're talking about is right here. So the axis here. So you want the unit vector of the axis, AC, you find that. You find the position vector and divide it by its modulus, you get the unit vector. So your unit vector is done. The force, dB, you find the position vector of dB, which you have, all right, and you divide it by its modulus right here. All right, so you divide it by its modulus and you multiply by AB, and you get this into what? Cartesian. See, done. And then now you can proceed now to do the triple scalar product. So the triple scalar product of MA is a unit vector, and the unit vector is written in the first line. This unit vector is the unit vector along the axis that you're talking about. The last piece is the position vector to the force. So they choose to use AB. The AB is here. And then you just do the multiplication. So it's there you go. So you have it. This is the position. So that is it. This is the force. This is it. And so you multiply to get this value, AC. And that is using AC direction. But as I said to you, you could also use another axis, another position vector to do it. So you could use, so MA, you could go AB times DB, which is this, same thing here. I'm just depicting it and do it over. And you get a unit vector and you go through and you do it. Right? You get the same value. You could use, so here you show you just do this part separately. So you could do the moment part separately. Right? You get that. Then you get the unit vector. When you get the unit vector now, instead of using this part here, so now you know what this is? Dot. What is this here? What this formula is showing you right here, so? So I'm showing you another way. What is this formula showing you here? Remember, what is this formula showing you right here? What this means here, so? UAC times MA. What is this right here? What is that mean right here, so? Can somebody tell me what this mean right here, so? Hello? Nobody?
That product of
That
the unit
product.
vector. Oh,
That product. So you're dotting the unit vector with the moment. So when you dot it with the moment, right? Right. So this is it would be it, and this is the moment. So it will be going this I times this one. See it here? It give you a minus, so the next one, the 0J times this one, it's going to give you a 0, not true. See it right here, so? And then the last one would be this K times 0 again, eh? Because the K down here, so it's 0. You should actually put it in. So it's only this part here work out, and you see you get the answer here. But this could be done in more than one ways. This could be done. The same problem could be work, because look, AB touches the force. AD, you could use the position vector of AD also. And you could use the position vector of CB also. Once the line touches the axis and touches the force, you could use that approach. So you have two options. You could use a triple scale. I didn't use the triple scalar product here. Note that. As I say, it's an alternative. I didn't use it. I found the position vector about O. So that was the position vector about the force. So I did that separately. Then I have the unit vector of this, and then I use a dot product between this one and that. And so you don't have to use the triple product, but the triple product is straight off. The triple product gives you the answer directly. Okay, just to get the unit vector of the line, and these are the other components. You do them one go, and you get it. Right? They have different options to use to find the moment about an axis. So the moment about an axis is tricky because you can use different methods to do it. So you have to keep your head on the body. When to use a dot product, that in the unit vector and the moment, right? All right. Remember the sense of the unit vector. So it's reverse sense of the unit vector because that telling you it reverses the moment showing a reverse sense of the unit vector. That's what it is. All right. And the last one, I think there's a last example there. Oh, these are practice example. So you can actually do these, right? It says here, determine the magnitude of the moment of the force F about the axis X, Y, and the Z axis. Solve the problem by using the Cartesian vector approach. And so you write the position vector of AB. So you look at this figure here. You have A, B down here, and this is AC up here. All right, so you must determine the magnitude of the moment of the force F about each one of the axes. So you have the x-axis. So you don't know, so you have to use the unit vector of the x-axis, which will be what? 1, 0, 0, 1, 0, 0. And if it is the y, it is going to be what? 0, 1, 0. And if it's the z, it's going to be 0, 0, 1. So you know the unit vector you can apply. So if you're using the position vector going from A to B, right? So you have that unit vector, you can work it out. It says the moment of F about the Z, the x-axis, for example. So the x-axis would be 1, 0, 0. So it's RA times F. So F from here touches so AB would touches the force straight. So you draw a line from A to B down here, and to touch this force line down here. So you could use this one, 1, 0, 0, because you already know the unit vector of this line right here. And then the position vector of AB would be this. It's right here. And then the force is in Cartesian, so you put it here. So that is using the triple scalar product. And you multiply it and you get it. 15 pound force. And that is for the x-axis. You can try the y-axis. The y-axis would work too because look, what's the unit vector here? It will be 0, 1, 0. So you'll get that probably a different answer because it's going to be 0, 1, 0, yeah, along here. And then you could still use AB, which touches the force. Yeah. So it's your choice. You'll get a different answer because that will be about the y-axis. About the z, you get a different one too, because the unit vector will be different. So you can try that, right? I'll leave you to play around with that. All right, so that is that. Now let's go back to your tutorial. That has been long. All right, so I'm gonna pause the recording here. Now let's stop, and we're going to shift gear a little bit. I know that's long. You're gonna need to go through that. Right, that's quite a mouthful. I know that. Don't believe I don't know. I need to take off all of these off the slide. Everything. All of these need to go. All of that. Don't want them on it. All right. Okay. So that is that. Everything need to go. Upper side. All right. So the tutorial now. Your tutorial question. You don't know anything about this tutorial question. Anybody work the tutorial question? Did anybody try it? Be honest. You remember this tutorial question? That's a tutorial question. Did anybody look at it? Look at it. And I needed to talk to me now, guys. We are not into malice. So don't come to the class and keep malice with me. I'm talking to you. Please talk to me. All right. So this is a problem that we are looking at now. And I'm looking for another software to use. You can go and get some water while I do the setup. for this section. We have a little bit over an hour. You can have 5 minutes break while I set up. And I'm gonna get some water myself. I'm gonna set up now. Here's my tool. Oh Lord, start with it. So everybody, pull up your tutorial question now. And that is what we'll be focusing on. All right. I do have a video on this, doing it full from start to finish. But so like the other class that I had today, I actually started it last week with them. But you guys have we never start this. So, all right. While I wait, I want everybody to tell me the coordinates. To start write out the coordinates. I will ask you for the coordinates for A, B, C, D. And read the question, please. So is a 3 ropes. 3 ropes is actually 4 rope. There's a rope that is connected at A. I have that crate. But that is not in the mix. We want the tension in rope AC, AB, and AD that have help to anchor it. AD is vertical. It's not on the ground. It's up in the air. And it looks like it's in the Z direction, and it's over the Y axis. So you can note that it is. So they tell you that the 2 ropes have anchored to the vertical wall B and C. So those 2 are on vertical wall, while the 3rd rope anchors to the ceiling. So it's up. It's not on the ground. Please recognize that the rope AD lies in the XZ plane. So it is telling you that it is vertical, that shaded one. So it's like it's directly over the XZ plane. So note that. Tell you which plane we're in. And then it says you have to determine the position vector along the 3 ropes, not including the rope which hold the crate. So we're excluding the rope that is 3 ropes. So we want the rope. Let's write them down. And I need your participation, please. We're not gonna have any tutorial if there's no participation. We need AC and we need AB. So we're going that direction. Comes here, and we want that. And we need AD. Those are the tensions that we need from the 3 rope. All right? And this is all about equilibrium. All right? So remember our lecture 4. All right, this has to do with lecture 4. All right. All right. Stick up in. I'm gonna get some water and I'm gonna close my mic for a little bit. Make sure you're all ready to go, you know. I'll be starting back in another 2 minutes. Okay. Are you ready now, folks? Ready to go back now? Hello? Are you with me now? All right. Nobody answering me. Hello? Are you all
Yes, sir.
sleeping? Yeah, man, I'm ready, you know.
Yeah, there, man.
All right. All right. So we're gonna be working together, you know. I've been talking for 2 hours. So this is why I don't really like online anymore, you know, because the student not talking to me. But this is tutorial, so I expect you to be working with me. So first thing, you need to find the position of find the coordinates for A, B, C, and D, and then we need to be able to write those position vectors. And from the position vector, we need the unit vector because the objective of this is to use our equilibrium equation, and we're gonna formulate some expressions using the force equation that F vector of F is equals to the scalar of the unit vector, the F, right? It's scalar value of F times unit vector, right? So for example, if we write in the vector of AC, we must have a unit vector of AC times the scalar value of the force. All right, so that's the approach we're using. And we're using that for every line. All right, because they are in equilibrium at A, they are in equilibrium. So we must note that there's an equilibrium is going on for each axis. Some of the force about the x-axis equal to 0. Some of the forces about y-axis is equal to 0. Some of the force about the z-axis is equal to 0. So we're using that. And so two things we need to do. We need to find the coordinates and we need to find the position vector. So come on, lead me on now. What are the coordinates of A? Please give them to me.
0, 6, 0.
0, 6, 0. Everybody agree with that? If you don't agree, call it out. B, please. X is what? Come on,
Zero.
guys. Huh?
Zero.
B is what?
Zero. Zero.
You sure? Look again.
Sir, -3.
Negative
Oh, yeah.
3. Yeah. I expect you to go through the question, and that's why I delayed, you know. Negative 3, at least have the coordinates. Negative 3 what?
0, 2.
So the y is 0 because it's over the y-axis, has no component there, and then the z is what? 2. All right. See now. Come, guys, please participate. X is what?
2,
2. Positive 2.
0,
Y is 0. And
3,
Z is what?
3. 3.
3.
Okay, good. And D is what now, guys? X is what?
0.
0.
Mm-hmm.
Y is 9.
Uh-huh. And Z is?
4.
But I agree. See it come up 4 in the Z there? Because this is in, it was told to your X's that these are on the ceiling. So it is in the Z, Y plane, and them tell us it in the Y, Z plane, the same thing. All right. So now we need a position vector of AC. So let's find the position vector of AC now, guys. Position vector of RAC is going to be equals to C minus A. So it is going to be what now, guys?
2,
So C is what?
oh,
C is 2, 0, 3, and A is 0, 6, 0. And so this is going to be 2I minus 6J plus 3K. You agree? and that is in feet. All right, if you disagree, tell me. That's the first one.
Sir, the position pointing to A.
Is what do I have there? Huh? It is the position point is what? Is what? Is
Towards A.
A is C is what? C is 203. Yeah. Let's check in A. A is it's supposed to be what now? This is what the value. It's 2, 3. Is it plus 2 or minus 2?
Sir, they said to A, sir. You have A to C, sir. And it's supposed to be
We have
A.
A to them say pointing towards A. Oh, okay. Well, I am finding AC. All right, I'm just finding what the question says. It says determine position vector of the 3 ropes. All right, taking the point vector pointing towards A. All right, so they really want the opposite, eh? They want the opposite of that would have been so I kind of jump in the gun. They really want RCA, which is going to be the minus of RAC, right? So that will going to be equal to minus times 2I minus 2J plus 3K. Yeah, that's really what they want. So it's minus 2I minus 6 plus 6 plus, sorry, minus 3K. All right. I'm a bit tired, so just watch me if I make it. All right. So there. All right. So that's really what they asked you for. All right. So we're gonna find what they asked. And then they say that you must find also BA, right? RBA. So RBA again is going to be A minus B. So let's find what they asked, and then we can take it from there. A is 0, 6, 0, and B is minus 3, 0, 2. And that gives you what now? 3 I plus 6J minus K. Is that correct? That's what you got? Body got that? That's BA. You agree?
Yes, sir.
All right. Next one is going to be the one, what's the next rope? What is the next rope they want? DA. The DA is going to be, it's going to be A minus D. So, all right, so this is going to be A0, 6, 0, and D is 0, 9, 4. So that typically gives you 0I minus 3J minus 4. Is that what you got? Everybody got that? All right. So that's the first thing you get. So you write those positions and you get those values. And then it says you express them into Cartesian. Those are the 3. Then it says determine the unit vector along all 4 rows pointing to A, pointing away from A. So that means they want the position vector that I start finding before. So if you're pointing to A, you want the reverse of all of these 3. Multiply 2 by minus and give them the reverse. So it means here now, trying to make it a little bit smaller so I can see them. So they really want R, A, C, going from A to C. So it's the reverse of are CA, right? And so we can write that. It is 2I minus 2J plus 3K. And similarly, other one are AB is going to be equals to RBA minus of it minus multiply 2 by it. So you're going to get 3I minus 3I minus 6J plus 2K. Right? Feet always. And the last one are AD is equal to minus R BA. I should be allowing you to tell me what to write, you know, but anyway, you know your reverse order, so this is going to be 3J plus 4K. Right? Alright, so your reverse order, everybody know that. How do we find a unit vector? Can somebody tell me the unit vectors now? The unit vectors for each line. We need them. So it's UAC. Let's say you have to find the unit vector along them going away from A. So the unit vector of the first one is going to be U is going to be RAC, the vector RAC divided by its modulus AC. So everybody know to do that by now. Nobody in the class should be scratching their head out to that. We do it often times. 2 square plus minus 6 square plus 3 square. And you take the root and you find a unit vector. Can somebody give me a unit vector of that one? And the next one will be UAB is going to be equals to minus 3I minus 6 plus 2K plus J plus 2K. Can somebody give me that, please? You divide that by its modulus. What's its modulus now? So that will be 9 plus 36 plus 4. How much is that? 47. 49. And so the modulus is 7, I think. And how much that work out to in decimal, please? I think the other one will be the same thing. 2I minus 2J minus 6J plus 3K upon 7. Alright, so you can give me unit vector of both of them. And the next one would be UAD would be equals to the unit vector of it. What was it? What was its position vector? Again, position vector would have been 0I plus 3J plus 4K upon 5. Alright. Can you give me those unit vectors, please? Thank you. Let me do a little cleanup while I work that out. Give me it in decimal, please. Thanks. I'll take it in decimal. This was 6. Minus 6. Alright, let me fix this one down. Okay. Come, guys, come. Night is coming, you know. It's night. I don't have all night. Give me the unit vector, please.
0.2857.
0.2850 I. I think you can go with, I'll take 4 decimal point. Let me tell you how much decimal point I want. That is AC. Let me tell you.
It's 442.
Hold on. Let me get the unit vector. Let me tell you how much points I want. I want unit vector. It's a AC is how much you say? What's the unit vector of AC is 0.286. 0.286.
0.428.
0.286, right? something is wrong right here. So this is supposed to be 7.
Yes, sir.
Okay, thank you. All right. So you could work with that too. All right, nice. So that is I. It's equal to that. And then the other one is going to be minus 1.
0.8571.
Okay. J. And then the next one would be plus
0.4286.
0.4289. You sure you're round off to her? 9, man. Check that. You're supposed to get 0.429. 7 into 3. You know what I'm saying? And I'll check it again.
Sir, 0.4286.
0.4. Let me see if I'm following the right one. Is AC we're doing, right? 4.4229. 9 is supposed to get approximately. So
Sir,
check.
3 divided by 7, sir.
Yeah. Hold on. Let's check that one. Divided by 7. 9, man. Now you're supposed to get 0.42857. Now that's you're supposed to get. And you round it off to 0.4. Where's my writer now? 0.429. That will work with 9. Or you could have 886 if you want. Right? But all right. We will work with, I think I'm comfortable because, all right, this is because this is going to be very mathematical. We're going to work with 3 decimal point. So I'm going to scratch this and work with 3 decimal point. I think that's sufficient. 3. So I'll work with 3. I'll work with 3. So this one I'm going to call it 6. Yeah, I'm going to work with 6. So 3 decimal points I'm going to work with. All right. So that would have been your unit vector. This is UAC. That's a clarity persons can see it. All right. That is that one. The next one now. What this one gives you, this one should give you next one, that is AB. AB should give you minus 0.429 I. And then the other one should give you what now? 0. What you get for this one? Eight five
8.857.
5 7 J. And is that correct? Is that so? Just check that, yeah. And then the last one you should get B. You should get
0.286.
yeah, so we get plus 0.286 K, and you put in, and that is it, of course. Oh yeah, but most importantly, and the last one, AD, is easy. First one is 0, and the next one is going to be 5 into 6 will give you it's 5 into 6 now. 5 into, what is it again? 5 into 3. Does that go? 5 into 3 should give you 0.6. So you should get minus, where is it? Oh, hold on. Is there one of these supposed to be minus? So it go. For AD, they're supposed to be minus, they're not supposed to be plus. They're supposed to reverse. I didn't reverse these. Yeah, these are minus. These are all minus. Minus, minus. So you're supposed to get minus 0.6. J minus 0.8. Yeah. Okay. So there you go. You have your unit vectors. Know that you have your unit vectors. So that is a big thing. These are what you want. These are your unit vectors. These are what you want. All right? These are your big thing that we want. All right? And similarly, these here. All right? So you need a unit vector to apply those special form. So from that, you're going to put them each line. Now you're going to apply the formula for each line. All right, so we're gonna copy this, and we're gonna have a nice little meal about it. So we have that. We have all three lines, three unit vector of the three lines. However, there's a third line. There's a last line we didn't do. The line that is intersecting is a line for here. We don't want the tension in this, but at least we need the unit vector for this line. All right? So the unit vector for this line would be 0, 0, 1. You agree with that? 0, 0, minus 1 going down. And that is a line that intersect all of them. So it would be, so for the Z, unit vector for the Z1, it would be 0 I plus 0 J minus K. Alright? Alright. And remember now we have one force that we don't account for yet. There's a 20 force going on in that direction. Remember it now. So we're gonna go over now. Let me do it again.
Sir, you can scroll back up, please. And look on AD, sir.
AD.
Yes, sir.
Where is it? AD. This is DA. And
Yes,
AD.
sir. The minus is for DA, sir. So AD
Yeah,
is supposed to
they're
be.
all of these are supposed to be minus. See them there? Minus. So they're minus.
Sir, DA, you got both twisted, sir. So,
Yeah, so when you reverse it down here, you're supposed to reverse it down here.
okay.
Oh, hold on. Let me see if it's the other way. Hold on. It's supposed to be reversed. The minus never come through here, so when the minus come through, I should have this as minus here. Hold on. Where is it? Is my writer. These supposed to be no minus. You got what I'm saying? Yeah, because DA was hold on. Let me see.
DA was negative though. The
Hold
J and
on.
the K.
Hold on. Let me just see. Hold on. AG. That means something was wrong. What was we finding before? Let me just. We were supposed to find D going to A. Oh, so we have it wrong there. Hold on. Oh, so it's supposed to be minus 3. Just checking the working. So it's supposed to be let me check what's going on here.
Sir, the DA is correct, sir, but the AD, when you change it to positive, sir, for the unit vector, you use minus when it's supposed to be plus.
Hold on. So it's supposed to be A minus D. Let me see if I have A minus D. I should get 0 minus. That's all? Yeah. All right. And then now, when I'm plusing them, hold on. Oh, so they're supposed to be plus? Let me check them something like good. It's supposed to be plus.
AD should be plus and the unit vector
Oh,
for
beautiful. Thank you. Yeah, so they're supposed to be plus. Yeah. Thank you. So say I just realized that I have some answer sheet that have some minor errors on them when we're going through. I'm going to have yeah, I just see now. So it's supposed to be, as we say, it's supposed to be plus 3J plus 4K. Yeah, man. So it was right before. Yeah, thank you. It was right before. They were, yeah, very right. Where's the block writer? Not coming block. Where is it? block, 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 one, block. All right, oh, the block. 3. Yeah, so that's it. Yeah, so it's yeah. So the AD would have been, what's the unit vector for AD? So it would have been plus. These are plus, plus, plus. Fantastic. Great. Good job. Good job. Let me correct something on my thing here. These are plus, plus, plus. Yeah. Thank you. Let us look on that. All this time I'm writing this thing, I never realized that. So this is supposed to be plus 2. Yeah. Plus, plus. All right, good. So those corrections, great. All right, so let me copy this and go to our new page. No delay. All right, so we want a new page. We're going to paste it. All right, so, all right. So that is what we have, and we're going to formulate our expression using, so for each line, we're going to write, and we're going from what? From A, going to those points. So for the first one, A going to C, your force would have been F A C equal to the scalar value of AC times its unit vector AC. Remember, this is scalar, and so this is equivalent to the same thing. You go, what's the unit vector of AC now? It would be F AC open bracket 0.286 I. Follow me now. 0.85 7 J. And I put in them J there, but so as to kind of just remind you that those axes there, right? And then now the next one would be plus 0.429. All right. So essentially, we could actually symbolize this now and saying that we could write this now. So each one of these will represent the X, the Y, and the Z out of each line. You realize that? Who see that? So we could write this as 0.286 FAC. All right. This is X minus 0.857 FAC Y plus this will be 0.429 FAC Z. You realize that? Agree with that? All right, so you don't know where I'm going. You don't know where I'm going, but I'm writing those. All right, so that's the first line. The second line now, I need to not go too far where I can't see the unit vector. So that is the first line. The second line, I could say, so along the line, the unit vector of the line times the scalar value of the force along the line. We normally, you could get the Cartesian of the line in the vector form, not true? Normally that's how we do it. You remember that? Okay. So for the next line, it will be FAB, which is going to be the same. The scalar value of FAC times the unit vector of AC will equals to now. Let's take it now. So what we don't know is FAC, but we have the unit vector of the line. So you put the unit vector of the line. So the unit vector would be minus 0.429. I'm right. I minus 0.857 J plus 0.286 K. And similarly, so we could actually write this as as minus 0.429 FAC X take out the I, minus 0.857 FACY, plus 0.286 FACZ, right?
Question, sir.
Mhm.
Why is it not FAB?
Let me see what you're right. Let me see what we're doing. Let me see. What are you saying? Oh, thank you. Thank you. Thank you. Thank you. Thank you. Lord, thank you. Very, very important. Absolutely important. Thank you. When you're tired, my dear, sometimes you write nonsense. And so we have to try and concentrate. Thank you very much. So it is supposed to be C. No, it's supposed to be B. This is supposed to be B. This is supposed to be B. Thank you. This is B. Thank you. This is B. And similarly, you could go again and write F A D. This is now going to be F A D. A D. And so this one now is going to be, this is supposed to be B. This is going to be F A D, unit vector of UAD, which is going to be 0I plus 0.6 J plus 0.8 K. And so this one will give you, so the first one is 0. So 0 FAD X plus 0.6 FAD Y plus 0.8 FAD Z. Right. Now, all right. So we have those three. Bear in mind that there's another force that need to be incorporated in one of these lines. But no, I want to signal them out and I want to show you something now. So what we've been working at so far is to get these expressions here. All right, hold on, where is it now? Where's my writer? I can't find it, it's gone. So these are two, fine. Yeah, so it's this. So this is representing one line. Which line is this? This is the AC line. Not true. All right, that's AC line. AB line is this one down here. Where is it? When the pointer, so I change the color, and sometimes I can't find it. Then you have another one. All right. So that is that. All right. And the last one is this one. All right. That is watch carefully. It is right. Now, if you go back up to here, you realize that at this point there is an intersection. There's an intersection where all of them meet right here, guys. And so there is a force coming down here. So in the Z, but anyway, we're gonna talk to you about it now. So look, let's go back to where we are. So all three lines have a force. So if you were to find the vector of all three lines, this is what your Cartesian vector of all three lines will be. Now we go back on to first principle and we say that there is an equilibrium along each line. There's an equilibrium representing each line, and so each line, there is an equilibrium statement that we make for each line, and we say that the sum of the forces, let me get a black writer because certainly can't find it. So the sum of the forces in the f of x equal to 0. sum of the forces in f of y equal to 0, and the sum of the forces in f of z equal to 0. If you look here now, on all our expression, we can single out that there is some coordinates that match the x-axis for each line. See them right here? This is the x-axis for each line. X-axis for each line. And similar, here's a coordinate match the y-axis for each line, right? Meaning that each line will have a y component, just like how it have an x component. I'm trying to find my writer. It's gone all over the place now. Where's the blue? Oh, it's right there. Can I do undo? Yeah, undo again. Yeah. All right. So it is here now. See here. So this is your for line AC, that would be your y. For line AB, this would be your y component. And for line AD, this would be your y component. And similarly, you would say, let me see if I can follow this one now. Hope I can find it. For your Z, for each line, here you go, 1. And then for here, and then similar down here. However, you remember that this Z, there's another line that is important. There's another line going down in the negative Z that we cannot ignore. And it's a line where they meet. Where all three intersect, there's a fourth line. So they normally write it, you will see it in your notes, that where F, where they intersect. So where A and where these intersect here. So you will CB intersect CB, right? Where CB intersect, if I could write it somewhere, where could I write it here? Where CB intersect, I need a block right now. C intersect or meet what's it? C and B, right? Where they meet, it would of course have a line, have a force that there. So the unit vector along that line would have been so there's a force, scalar value for force, and there will be a unit vector similar. So the unit vector, remember that the force going down in the Z was 20, but its unit vector was 0 I plus 0 J minus 1 K, because it was going down. So that would typically give you an expression to say that there is a 20 I, which is 0. That is 0. So these two are 0, and the other one will be 0. So it will be left with just minus 20 K. 20K is saying that in this direction there's a minus 20K. All right, so remember that. Keep that in mind. So there's a fourth expression that needs to be taken into consideration. So for the first one, we look for everything in the X and we put them and we group them together. So I think I need to move something here. They're a little bit too close. So we're gonna do the X. I'm gonna move that. All right, I'm gonna do the X first. So some of the forces in the X now, you could write that 0.286 for FAC, right? You already know it's X, so you don't have to write X beside it. That's for the first line, and the next line would have been, make sure I write the right value. That would be minus, second one, 0.429 FAB. Right? It is already X, you don't have to write anything else. And the last one would have been plus 0. The last one is 0, equals to 0. So remember the equilibrium equation, everything must be equated to 0. So each line is in equilibrium for the x. So in the x direction, all of that can be summed to the 0 for each line of a component there, and you equate it to 0. All right, back to equilibrium. And for the y, change this one to y. Let me fix that good. And for the y, similarly. So for the y, it would be, let me see if I can find them. Not too far. So for the y, it would be that's for the y components now. It would be minus 0.857 F AC. That's one of the line for y. What's the next y component now? It will be AB component, it will be minus 0.857 F AB. And then the last one, AD line would be, where is it now? See it right here, plus 0.6 F AD Y. Right? And they're all equal to 0. And the last one now, sum of the forces in the FZ equals 0. Let's write this one. So the Z now have everything in the green, plus the fourth line that I tell you about. So it would be, what was the first one? What was that one? It's supposed to be, is it minus 0.429 F AC? Agree with that one? See it up here? Then the next one would be, is it plus 0.286 F AB? And the last one would be plus 0.8 F A D. Right? Did I put y on that? You don't have to put any y there. Let me just take off the y off of that. Right? And then now you have to consider the fourth line here. That there's a minus 20 going in that direction. So you need to put it in. Let's put in a minus 20. There's minus 20. Don't put any k or anything between it. It's minus 20. Right? That's the minus 20 equals to 0. If you don't put a t in it, be wrong, because you have a force going in that direction. You know that force going in that direction. So all lines, and what you end up with now is a simultaneous expression. We have three expressions. And how do we solve? If you notice, each line, all the component, one of the components out of the first line gone. AD, that gone. So for I have AB, this is the simplest expression. So this is now equation 1. So I'm going to write it on this side. So this is equation 1, 2, and 3. So your objective now is to solve for all of the tension using this is a simultaneous equation. And you have to solve this using, how do you solve this? Is it elimination or substitution? Which one do you think?
Substitution, sir.
Right. So you have to look at it and say which one is the simplest one to approach. And so you could go about and transpose equation 1, right? In this case, equation 1. If you transpose our equation 1, we have AB and you have AC, right? And I'm looking at my sign, yeah. And they are pretty much okay. And so you're going to do some substitution thing here. So you can actually put it, let us see if we can move it somewhere else. And you tell me how you solve this. Next one. All right. So you go right here. All right. All right. So you have those three equations. And you're going to go ahead now and solve it. So you're going to do some transposition. So you're going to substitute. So you go to equation 1, you're going to form a fourth expression. So you could say 0.286. Oh Lord. My writing is atrocious here. Let me see if I can get that writing. All right, that one. Let's see. So you're gonna get 0.286 F AC, you carry it over equals to 0.429 AB. You can choose to transpose it for one of them. Which one you want to transpose? AC? So you can say for F, AC. And so that becomes FAC is going to be equal to 0.429 divided by 0.6. And this becomes FAB. Right. Watch that work out. Can somebody work that out?
1.5, sir.
So it give you what? 1.5 FAB. All right. Now that you have done that, you have two other expressions. So this is now equation 4. You could say to yourself, all right, I need to drop this in either equation 1 or equation 2. I would work with equation 3. You know why? Equation 3 has a number there, so chances are to start giving some dividends. Is that your thinking? So you want to make some homogeneous thing. I may have to do 2 substitution, right? So one of the first thing, I'm going to substitute it in equation 3. That's my next step. So I'm going to, and you're right, substitute equation 4 in equation 3. So let's try that out. So you will go anywhere you have AC, you put that in. So it will be 0.429, open bracket, and you put 1.5 FAB. Now you have to be very careful here, guys, because sometimes it can really, if you don't do the substitution right, you just continue working, and it will not drop out. So it's done by inspection, you learn them over a period of time. So the other one, you would have what now? FAB plus 0.8 FAB minus 20 equal to 0. And what this work out to? Can I simplify this expression for me? All right. No. What's it simplified to the first part? Simplify it now, guys. You need to be working, you know. How much are you there? Only 14 persons leave. Only 13 persons leave. The rest of them gone on the yard. Them hang up. Them can't bother. Them bored. Come on, guys. Yeah, we don't have much time.
All right, sorry. First part was 0.644.
FAC, FAB, right?
Yeah.
Plus 0.286 FAB plus 0.8 FAD minus 20 equals 0. And you can still simplify that a little bit more. All right. If you simplify that a little bit more, simplify now. Add the two of them together. What you get now? The AB is
No. 0.9.
0.9 flat.
0.93.
Yeah, man. You have to maintain your thing. Plus 0.8 FAD minus 20. You probably want to keep it that way. Right? And then so you have that now. And then you're gonna take the same thing and you're gonna substitute it. Why is it getting so small? The same thing you're gonna take and you're gonna substitute in equation 2. So equation 2 was what now? This little guy right here. This one right here. Alright, I'm gonna drop him right where we can see. Yeah, not even changing anything. And so you're going to substitute equation 4 in equation 2. So you can make some little statement, right? And you're going to proceed to do it. So it's anywhere in, what is it that we substitute again? AC. So AC was this little thing up here. I need to be able to see it. So we're not looking for it and don't have it. Oh Lord, we're running out of space. All right, I'm gonna make it a little bit smaller rather than carry. So, okay. So here we're gonna do the substitution. Let's go through now. So, it is going to be minus 857, open bracket, 57, and it is going to be 1.5 FAB. All right. What's the next part now? Where am I now? So anywhere AB is, you take it out. And then the next one is going to be 0.857. You have to concentrate in this here, guys. And you put back this one. Plus 0.6 FAB equals 0. What does one work out to be? Come, guys. 0.857 times 1.5. Minus
so
what?
now, is that a negative
Minus 0.857 times 1.5.
negative 1.286.
1.286 FAB minus 0.857. Let me see if that is correct. Is that equation correct? Yeah. FAB. Please check the equation, because if we have anything wrong, it will never work out. Plus 0.6 FAB, right, equal to 0. Simplify that for me now, please. We run out of space because a lot of writing. So you add the two of them together. You're supposed to get them as minus. Right? And this take a little bit of doing, guys, but you can do it. You have to
Negative
concentrate.
2.143.
Negative 2.14 F. Are you sure you have no more decimal?
3, I said 3. 2.143.
Right? Plus 0.6 F A D equal to 0. So you see this equation now, guys, you're gonna take them and you're going to solve it. And when you're done, you go back to that equation 4 and find all of the values. So you're gonna take that one and you're gonna take this one. Take these two now and you solve them. All right. All right. So we drop another page. All right. So them two equations. You take them, put them together. So you have 0.93 FAB plus 0.8 FAD. Some people gone to sleep on me. Equal to 0. And then the last one would be minus 2.143 FAB. And guys, you have to check back your work in here, because if there's any error in it, it will not drop out. You have to try not to make any error. Right. So right here, so now you have a simple expression just in AB and AD. Any suggestion? What would you do right here now? Same substitution. What would you do to solve it? You think you would rock with the last equation and make that and solve it for what? AD? You think so? That's what you would do? Give me a suggestion. So if you were to transpose AD in the last expression here, so you would get 0.6 FAD equals to 2.143 FAB, and you transpose FAD equals. So this is it's lengthy. I will admit that, guys, but and there's no other way around it. Come up, I need some space. I wish I could tell you there's an easier route. 6 F A B. What do you get for that?
3.572.
Says 3.572 F A B. And you take that now and you put in the first one. Let's see what you would get here. So you would get anywhere AD is, you put that in. So it will be 0.93 F A B, leave that as is, plus 0.8, open bracket, 3.572 F A B. Alright, right, close bracket, minus 20 equals 0. So you have everything there is in AB now. Work it out and tell me if you drop out, please. Right, you can try it another way. That is one way. It's lengthy. I won't kid you around. What do you have there now? I don't multiply this and add them and tell me what you get for FAB. For FAB, right? Just give me one figure.
All
What you
right.
0. What? Is it 0?
3
0.8 times that. How much?
3.788.
3.7 what?
88.
88 F
AB.
AB equals to 20. That's what you got? A transpose of AB. And what are you getting that now? Let's see if that is working out. If you get the answer off, it means you have to go back to and check. How much you get?
5.28.
Yeah, that is correct. 5.2. But it's a long go, guys. And if you make any mistake, you're out. In the cold, you have to start over. And so you get that now. And then now you can say based on that, FAD is going to be equals to 3.572. Because remember, you have it up here. And you have FAB beside it. You multiply it by 5.283 because you're coming from here. This statement up here. So you're coming from all of that. Right? You know what FAB was? FAD was this. FAD is equals to 3.57 times AB. So you multiply AB by it and you must get the answer. What do you get for this part? So it's AD that you're getting. You should get about 18 something. 18 point what? 868, something like that.
Oh, sorry, hold on. 572 times 5.2. 18.871.
Right, and that is pounds. And the last one, you go back to your very original statement. You remember your original statement? It's just long, guys, but it will work out. What was your original statement again when you just start transpose? See it here? This one right here. Equation 4. You could label the other equations here, equation 6 or equation 7, whatever you want to call them. When you finish these down here. Whatever you want to call these, equation 6 or equation 7, whatever. So if that was 4, you end up with probably equation 5 and 6, something like that, right? So these are
Yes,
more, we should have labeled them equation 5 and equation 6. So you could actually interpret them when you're doing the insert. And this would call equation, this is probably equation 7 down here. This probably would end up to be equation 7. Right? Yeah. And so the last one, I will say what it is again, 1 point, where is it again? 1 point, I'm trying to remember it, 1 point something. See it here. Equation 4. Yeah, this is what we want. Let me just go with it. Where did I? Equation 4 is this. Come on. So equation 4, can you want only thing you find out is AC. So FAC is equals to 1.5 times AB. Value. What is AB now? Can you have AB already? AB is 5.283. You drop it in, how much you get for that one?
7.925.
7.924.
Yes,
About that.
4.5.
Yeah.
4.5.
Right. So you see, it's a long process, guys, but it work out. It's long. I will not tell you that it's not long. Alright, but if you after a while you're able to do it shorter, it's because I'm explaining, you know exactly what to write, and it take your time. It is unit vector times. So what you do? You go and you identify each card you need to get the unit vector up there. You multiply it by AB right through for each card, for each component. And you do it for all 3 lines. But in this case, you know for the Z, in the Z direction it's going there. So if any one of them have a force going in that direction, you need to incorporate it in that line. You understand what I'm saying? So it's in the Z, you have this 20 coming down, so you have to incorporate it. There's a minus 20 going down. So you have to put that into the Z line. Because if you left that out of the Z line, so it meets. So in other words, what we're actually saying here, this AC and AB line intersect right here. So because of that, we can get this expression here. Here's the equation that I found because of that line. So somewhere down here. Where is it? I know I wrote an equation right there. Where's that I wrote? Right here, this one. It's really AC and AB meet. Give you that line here. Because you have the unit vector going here with them meet. So this is 20 times its unit vector going that direction. So you could also say is where AD meet, intersect, where they all intersect. So there is a line going down here. Alright? So in that line is 20 times its unit vector. So any time they give you a force, if it is in the Y direction, it's going to be the Y component to be there times its unit vector of that line. Whichever line you give you a value in, you need to incorporate it in your expression. And so that is it. So we are able to do up to expression. Where are we? So we express the rope in the tension. Let me see what we found here now. So we were able to find, oh Lord, guys, you know that our recording was off. I didn't remember that I didn't put it on. Oh my. Oh my. I didn't remember.
Sir,
Okay.
been recording this whole time.
Let me see. I never I thought that I was recording up to
Sir, it was.
oh, okay, but I'm not seeing anything scrolling here.
Sir, we're seeing it there.
You're seeing it?
Yeah, the recording symbol at the top.
Sir,
Oh,
been
okay.
recording this whole
Okay,
time.
because I don't see scroll. Okay, so I was recording. All right, fantastic. So what we're really saying, we did up to, so we find the magnitude of the tensions in all 4 rows. So you have to express the tension in AB in terms of Cartesian point away from A. We did that. Determine the magnitude of tension in all 4 rows. Right? Express the tension in rope AB in Cartesian vector passing away from A. So we haven't done D and we haven't done E. All right, what I'm going to have to do, I think I'm going to have to post a video of me working the rest of it. Working the full question. Obviously. Another option is when the class is behind, they need to commit to an online session where I can bring them forward. So That's also a concern. So let's see how I bring them forward.
Sir, what about Thursday class, sir?
What about Thursday? All right. Let me stop this recording because I'm gonna
Sir, can you scroll
oh,
down?
yeah, pardon me?
I was asking you to scroll down. I was writing. Yeah.
Thursday class, let's stop recording. Am I stop? I see recording.
We're still recording.
All right. And let me pause.